Okay, we continue with duality. Let's consider a linear programming problem in this form. I talked about this in the previous lecture. Nevertheless, let's just start with that. All the constraints are of greater than or equal to form, possibly including non-negativity or whatever. And if you happen to have equality constraints in the original problem, you can always express them by a pair of inequalities of opposite sense. And then you multiply one of those pairs by -1 to get everything into this particular form. So here, suppose we choose a row vector W. By the way, A here is, say, k by n. So it has k rows, n columns. And so we want to choose a W which has as many elements in it as a vector, row vector, as there are rows of A matrix, okay? Such that W has non-negative components and W times A gives you C. This is how you choose your C. Of course, assuming that you are able to do so. Okay? So once you do this, so if you do this, then for any feasible, thank you, for any feasible x to the primal problem, we have the following. What do we have? We have the objective value, Cx. But because of our choice of W, C is actually WA. So times X. And then, of course, if you get rid of the parentheses, you may first multiply A with X and then pre-multiply by W. Okay? But AX, due to the feasibility of X, is greater than or equal to B, which means that this whole thing is greater than or equal to WB. Okay? So that tells you that WB is a lower bound. Okay? WB is a lower bound on the objective value of the minimization problem for any feasible X. Okay? So now this works for any W. As long as the two conditions, W non-negative and WA equals C, is or holds. Okay, as long as these two conditions hold, you've got that. By the way, where do we use W greater than or equal to 0? We use it also here. Maybe we should add that here. A non-negative vector times another non-negative vector, which is greater than or equal to some other vector, will give you that inequality. It's just that. It's just the dot product of two non-negative vectors. Okay. All right, so this works for any W for which these two conditions hold. So if you want to get the best lower bound, you want to push this lower bound as much upwards as possible. Okay? So to get the best lower bound, we want to choose W so that WB is as large as possible while the conditions non-negativity on W and WA equals C are maintained or satisfied. Okay? So this gives rise to the following linear program. You want to maximize WB, that's because you want to make it as large as possible, while maintaining the conditions WA equals C and W greater than or equal to 0. That's where the dual comes from. This is called the dual of the primal problem that we stated here. Okay? So one is a minimization, the other one is a maximization. And the non-negativity on the W is, of course, used in some appropriate way to obtain this lower bound. Otherwise, we could not get that. And once you get the lower bound, the fact that the lower bound is a valid lower bound for any such W, you want to push it up. And that's why you are maximizing it. All right, so that's the dual of the initial form I gave you there. Let's look at the canonical form now. Let's look at the canonical form minimization problem and its dual. In the canonical form minimization problem, you're minimizing Cx subject to Ax greater than or equal to Bx non-negative. That's your primal problem. And the dual of this we already know, or some of you may already know, but what you can do is this, you can rewrite this in the following way. Minimize Cx. You just make it look like the initial problem I gave you at the beginning, subject to an identity times x is greater than or equal to Bn 0. Okay? So this is in the same format as the initial problem I gave you. So the dual for this is you want to choose now a W which corresponds to all rows of A matrix here, or the new matrix here. And in that case, of course, you may associate certain components of the chosen vector with the A part, other components, say call them V, with the second part. So you want to choose a row vector WV which has as many components as there are rows in A and identity together. Okay? Some of you seem to be a little bit lost. Nevertheless, I'm just going to continue. Choose W and V non-negative in each component such that WV times AI gives you C. Then, again, for any feasible X, of course, P is here, say this P, let's call it P prime. Okay, for any feasible X feasible to P prime, we have then Cx equals, C is expressed by this, which is WA plus V. That's what you get for C times X. And that, of course, gives you WAX plus VX. Now, what do we know about AX? It's greater than or equal to B. W is non-negative. X is greater than or equal to 0. V is also non-negative. So this is greater than or equal to WB plus V times 0. I'm just replacing each of AX and X with B and 0 respectively. Okay? I'm replacing each column vector in the dot products by something that are less than or equal to themselves. Okay, so this is what you get, which is, of course, equal to WB. Again, CX is bounded below by WB, the same thing. Okay? Of course, this gives rise to, so you want to choose, again, the best lower bound, which means that you want to maximize WB subject to these conditions. W times A plus V times identity gives you C, and W and V are both non-negative. Okay? All right, so an equivalent version of this, if you think of the V vector as a vector of slack variables, because that's what they are, okay? Then, of course, you are maximizing WB. You can just drop the slacks. And once you drop the slacks, you've got WA less than or equal to C with W non-negative. And that would be the dual of P prime. So let's just call it D prime. Okay? Of course, this is also the dual of P prime, except that when you look at the dual of a given problem, you want to use the same data as you have in the initial problem. The data here is CAB, and you want to use the same data here. You are still using BAC as your data, except that the rows of B and C are swapped. Okay? Of course, there's a reason for that, and the reason is what I tried to explain to you. Okay, so that's for canonical form minimization. For canonical form maximization, you can argue in a similar way. The problem in that case is, say, maximize CX subject to AX less than or equal to B with X greater than or equal to 0. That's your canonical form maximization, which can be rewritten in the form as maximize CX subject to AX less than or equal to B minus X less than or equal to 0. I want to make all the constraints of the same sense. That's why we're, bothering with that. Again, you want to choose W and V, W associated with the first part, V associated with the second part. Which is non-negative in each component, because when you multiply the constraints with these W's and V's, you want to maintain the inequalities. If you have a switch of sign, or if non-negativity is not maintained, of course, some of the inequalities will reverse. Okay, that will make the lower bound invalid. In other words, we want to get to a lower bound. Okay, so choose WV greater than or equal to 0 with WV times the matrix A minus identity, producing C. Then, for every X feasible to P double prime, we again have Cx, which is now equal to WA minus V. I'm just multiplying them out. C is this much now, which gives you WAX minus VX. Now AX is less than or equal to B here, W is non-negative. X is non-negative, or minus X is non-positive. And V is also non-negative. So this will give you less than or equal to W times V and plus V times 0. I'm taking minus X as non-positive, so you replace it with 0, which is equal to WB. So what do I have? WB is an upper bound. That's because the constraints were in a different format. That's why, things have switched around. And for this reason, this gives rise to a minimization type dual problem, because you want to minimize the upper bound, or you want to push it as further down as possible. Okay? So you want to minimize WB subject to this condition, WA minus V equals C, with W and V being non-negative, which is equivalent to the minimization of WB subject to, well, just think of V as a vector of surplus variables, which you subtract from WA. So if you drop the surplus variables, you have this kind of constraints with variables only in W. Okay? That's your dual. Anyway, it's always the same reasoning. So I'm not really going to go through each one separately, except maybe we should do it also for the standard form problem. So let's do it for standard form. So in that case, you may have a minimization or a maximization. Let's just take it as a minimization. And that's your standard form problem. All right, so in this case, I have equalities as well as non-negativity. So what I'm going to do is I'm going to associate a vector of multipliers by W by for the first equality type constraints, and V for the second part. Now, if you look at this, Wi will be associated with the ith constraint here. Each component of W is associated with a given row of the A matrix. So when you multiply both sides of the ith constraint by the respective Wi, of course, it doesn't really matter what Wi is. As long as it's non-zero, you get equality on both sides. For equalities, you don't need any non-negativity restriction. Okay? If it is 0, you still get equality, except that, of course, it makes both sides disappear, which is not very good. Nevertheless, it works. Okay? So in that case, W is free. You don't have any sign restriction for that reason. In the other one, of course, you want non-negativity, because the inequalities will be switched if you don't have that condition. For that reason, you want to now choose WV as a vector with only V restricted to non-negative values, and you want still WV times A. What do we want here? Okay, in this case, things are a little bit different, actually. Just a second. I still want to express the C vector as a linear combination of the rows of A and identity. Okay? So here we've got the A matrix with many rows. Let me just do it this way. A1 up to, say, A. Let's make it AM. Okay? Let's assume in the standard form we have M such constraints. Then you have the unit vectors, E1 as a row vector. So let me make it transposes. My unit vectors are typically column vectors, so I just make it row vector up to the last one, En. You have a multiplier associated with the first row, and so on and so forth. Wm is associated with the last row of A matrix. Then you have V1 associated with this one, Vn associated with the last one. Okay? What do you want to do? You want to multiply these rows with the associated multipliers to get your C vector. You're trying to express C as a linear combination of the rows of the constraint matrix. Okay? All right, so the additional condition here is you still want to have WV times A and identity giving you C. Okay? That's what you want. If this is the satisfied, then for every x feasible to, I don't know, is this P triple prime? Where are we now? P double prime, P triple prime, okay. For any x feasible to P triple prime, we have Cx, which is again equal to Wa plus V times x, which gives you Wax plus Vx. Now Ax is equal to B. W is unrestricted in sign, but I don't care because we're just replacing it with B here. Okay. Plus Vx, but x is non-negative, and V is also a non-negative. So this is surely greater than or equal. Change that to greater than or equal now. V times 0, which gives you WB. So again, what kind of a bound do I have? WB is a lower bound. Because the initial problem is minimization type. That's what we wanted to get. So the dual problem that arises from this, well, you want to push the lower bound as further up as possible. This gives rise to a maximization type problem where you push WB upwards subject to WA plus V is equal to C with V non-negative, which is equivalent to the maximization of WB subject to WA less than or equal to C with no sign restriction on W. In other words, I'm just dropping V out of the problem because it's just slacks. So once you drop them, this is what you get. For that reason, whenever you have equalities, the corresponding variables W's are unrestricted in sign. There's a reason for that. Okay? Okay. So the basic idea is to always express the C vector as a linear combination of the rows of the constraint matrix. And once you've got that, you have the proper inequalities or whatever you have, which in a natural sense gives you rise to a different linear program, different only in structure, but the same data. For mixed forms, let me just give you a few pointers here. If you have a canonical form constraint in one problem, so we're considering that primal dual pairs. By the way, the dual of the dual is always the primal, so maybe you should make a note of that. If one of the problems has a canonical form constraint, if some constraint in one problem is of the canonical form, then the corresponding dual variable in the other problem is a non-negative variable. So the constraints of one problem are associated with the variables of the other problem, and a canonical form constraint gives rise to a non-negative variable. Also, if you have a non-negative variable in one problem, it gives rise to a canonical form constraint. Okay? What's a canonical form constraint? It is a less than or equal to for max and greater than or equal to type constraint for minimization problem. How do I remember that? Well, I have a way of remembering that, but I'm not going to tell you. You figure your way out, okay? Okay. Okay, if you have the reverse canonical form constraint, which means for a maximization problem, the constraint is greater than or equal type, and for minimization, it's less or equal to type. In that case, of course, the corresponding variable happens to be non-positive. Also, a non-positive variable corresponds to a reverse canonical form constraint. And if you have equality type constraint, then the corresponding variable will be unrestricted in sign. It's unrestricted variable, and also an unrestricted variable in one problem corresponds to an equality constraint in the other problem. Okay? So, if you remember this tableau, you can actually find the dual of any problem. So let's do an example. Suppose I have a maximization problem. 2x1 minus 3x2 plus 7x5 subject to, what else do I have? Let me have a constraint which gives you, for example, 2x1 plus 5x2 minus 4x3 less than or equal to minus 8. Then we have 5x2, well, not 5, 4x2 plus 5x3 minus x4 is greater than or equal to 6. Six x1 minus 3x3 plus x5. Let's make it 2x5 is equal to, say, 10. Let's make x1 and x5 non-negative. x2 and x3 are non-positive. and x4 is unrestricted in sign. Okay? Suppose that's the primal problem. Now let's write down the dual of this. For the dual, you associate a variable with each of the constraints. So let's associate W1 for the first row, W2, and W3 for the remaining rows. Now, the dual problem is going to be a minimization, because whenever you have a maximization in one problem, the other one is always a minimization. And the right-hand side, this is the b vector, become the cost coefficient. So minus 8 times W1 plus 6 W2 plus 10 W3. That's your objective function. Subject to now you're taking the row vector W1, W2, W3, multiplying it with the A matrix that you see here. If you perform the multiplications one column at a time, you get W1 times 2 plus W2 times 0. The coefficient here is 0, plus W3 times 6. So that's going to give you the first constraint. And the right side of that will be your C1, which is your 2. So that's what you've got. The second column gives rise to 5W1 plus 4W2 and minus 3 on the right side. Then minus 4 W1 plus 5W2 minus 3 W3. Right side is 7. Then we have minus W2 on the right side we have 0, and then we have, what do we have? 2W3 and on the right side we have again 0. Now the variables associated with these constraints are x1, x2, x3, x4, and x5. Okay? If you're moving from the dual problem to the dual of the dual, which is your primal. Now, x1 in the original problem is a non-negative variable, which means that this constraint is supposed to be in the canonical form. This is a minimization, so the canonical form is greater than or equal type. Okay? So, the constraints are, or the sense of the inequalities are filled out later. x2 is non-positive, which means I reverse this inequality. x3 is non-positive, so you reverse it. Reverse of the canonical form. x4 is unrestricted, which means this is equality, which actually tells you W2 is equal to 0, so you can drop it out, but nevertheless, that's what the constraint tells you. And x5 is what? Non-negative, which means the last constraint is greater than or equal type. Okay? And then finally, we need to also give the senses of the restrictions on the variables. Now, this constraint for a maximization problem is canonical form, which means W1 must be non-negative. Okay? The second constraint is reverse of canonical form, so W2 is less than or equal to 0, and W3 is unrestricted. Anyway, this is the dual problem. Okay? I was using this table here, just in case you wonder where all this comes from. That's all. Of course, this table also comes from the initial derivations we have, except that I don't have that much patience to derive all of them, okay? But you can actually do it on your own. Okay, so let's talk about some duality theorems. So let's talk about the weak duality theorem, which actually is nothing but what I already gave you in the motivating problems. For a primal dual pair of problems, pair of linear programs, for any pair of feasible solutions to the primal and dual problem, the objective function's value for the minimization problem is bounded below by the objective value induced objective value of the maximization problem. Of course, I'm talking about the objective values that are induced by the feasible pair of solutions, okay? So let's see how we can prove this. I'm going to work out the proof only for a specific case of primal dual pair because, you know, the general case is it works for any pair. Nevertheless, let's just consider as an example pair, okay? You should be able to also work it out for other pairs. Consider, for example, the primal dual pair where the primal is, say, minimization of Cx subject to, say, Ax greater than or equal B. And the dual is maximization of Wb subject to Wa equals C with W greater than or equal to 0. This was the initial pair I gave you at the very beginning. Okay, so for this pair, let's just pick a pair of solutions. Let X bar, W bar be a pair of solutions that are feasible to P and D respectively. Okay, so given this, when you look at the objective function value of X bar, it's Cx bar. This is equal to, now W bar is feasible to this problem, so it's going to be W bar times A, which gives you C X bar. Okay? Of course, I was using the dual feasibility on W in writing that equality. From here, what else do we have? This is, of course, equal to W bar times A times X bar. Like that. And AX bar is greater than or equal to B due to the feasibility of primal. So we are using primal feasibility for this one. And W is also greater than or equal to 0. And I'm using dual feasibility here. W bar is dual feasible to the dual. And because of these, this is greater than or equal to W bar times B. And that is the end of your proof. You just showed it. Okay? It's a lower bound. Did I do it right? This is the, yeah. The minimization objective value is bounded below by the maximization's objective value. Okay? Of course, you can work that for other cases as well. Strong duality theorem. For a primal dual pair, if one of the problems has an optimal solution, then the other one also has. So does the other one. And the objective values are equal. Okay, I'm going to prove this for a particular case, but before doing that, maybe I should give a corollary to the weak duality theorem. So let's go back to the weak duality theorem and let's write I left it blank for good reason. So let's just write a corollary to this. All right, so the first corollary is the following. If X bar, W bar are feasible solutions to P and D respectively, primal and dual respectively, then with such that their objective values are equal, then they are both optimal. They're both optimal to their respective problems. Well, this is immediate from the fact that optimality means, for example, if X star is an optimal solution, then its objective value for a minimization type primal problem is always less than or equal to the objective value of any feasible solution. So this is any feasible, and this is optimal to the minimization type primal problem. Okay? We know that that's the situation. we also know the following. Cx bar is bounded below by W bar B, well, they are actually equality in this case. Now, let me take any feasible solution here, feasible x to the primal for minimization type primal. Cx will be bounded below by WB for any feasible W. In particular, W bar is an optimum solution, so it's feasible. Okay? And of course, this is already equal to Cx bar by assumption of the theorem or of the corollary. Which means, of course, Cx is greater than or equal to Cx bar, which is what the definition of optimality or being minimum means. Okay? So that's why it's immediate. You may also show the same thing for duals. So that's the end of your proof. Such corollaries don't really need proofs, except that, of course, I may ask them in as a side question, in which case you have to give the proof. But they are quite immediate, actually. What is the second corollary? You are students, so you need to work them out. All right. The second part, corollary 2. What is the corollary 2? Well, if one problem is unbounded, then the other problem is infeasible. This is again immediate. If the minimization type problem is unbounded, then the optimal cost is minus infinity. If the other problem happens to be feasible, then that would give a finite bound on the minimization. But that's not what happens here. So you have to have infeasibility. Okay? Again, it's immediate. All right. So let's go back here. I'm going to let you go in a few minutes, except that maybe I'll just leave it to the next time. Huh? We're already out of time, and you're getting impatient as far as I can see.